In this section of the program, we are supposed to review the classic solar system tests of general relativity. These are tests of the theory carried out within the solar system. They are the old tests of general relativity, and all of them, as we are going to discuss, involve low velocities and weak gravitational fields. These are the kind of fields that one can find in the solar system, and also the kind of velocities that one finds in the solar system as well. These tests are the deflection of light by the sun. You remember this famous story about the total eclipse of 1919. The gravitational redshift, which is something that we already discussed when we studied the first consequences of the Einsteinian equivalence principle. The precession of the perihelion of Mercury, which is a consequence of the fact that the Keplerian problem has been perturbed by terms that come from, if you want to call it, relativistic terms that come from general relativity, and the radar echo delay, or also known as the Shapiro delay, which is an experiment in which one sends a signal. Okay, it can be a light ray or a radar signal to a planet which is on the other side of the solar system, across the sun from our position, and the signal comes back, and in both cases it passes by or close to the sun, and this produces a delay, in the sense that if you compute the time in which the signal takes to go one way and return, and divide the distance by this time, you don't find the speed of light. It looks like the light has gone at a smaller speed. This is something that we can discuss later, okay? Because probably you have heard so many times that the speed of light is an absolute, and so on, that this kind of result can be surprising, and it may look to you inconsistent or contradictory with the principles of general relativity. In any case, these four tests are really tests that are performed with weak gravitational fields and low speeds. And then, since in the program a bit later we are going to study this parameterized post-Newtonian formalism, which is adapted to weak fields and low speeds, we can recover all these effects in that formalism, which is much better, because it includes not just the general relativity but any other theory in the same class. Okay, a metric theory of gravity that can be represented in the low speed limit, weak field limit, as in this parameterized post-Newtonian framework. Also observe that the gravitational redshift has already been discussed, and also in the previous section we have computed the precession of the perihelion of Mercury. So these two things have already been discussed. The only things that we have not discussed really are the deflection of light and the radar echo delay. If you look in the lecture notes, you will see that all these points are discussed and the computations are done. In fact, except for the gravitational redshift, because that was already done in lecture 2. And okay, the precession of the perihelion of Mercury has been computed in a different way, in an alternative way. So all these things are computed there in the lecture notes, but we are going to compute them in yet another form in the next section of the program. So I will skip entirely this section, because otherwise there would not be enough time to explain everything. You are not going to miss any content, okay, because we are going to study the deflection of light by the sun and by any other planet, any other source of gravity, the precession of the perihelion of Mercury, and any other object, and the radar echo delay. but in a more general context and using a different formalism. If you want to check the calculations in the lecture notes, you are free to do it. You will always learn something. I think I have used Anthony C's book, and the computations are the same that you can find there. However, I think the framework of this parameter post-Newtonian approximation is much more powerful. In that section, I have followed the book by Eric Poisson and Clifford Will, which is an excellent book that I recommend you, which is a book specialized in approximate solutions to general relativity. And that's the approach that we are going to follow. We will study all these effects, but in that framework.